Hi, you probably clicked this video because you want to see how to extend titration to fractional heights. So a quick revision about titration. We could write it with we can write it with two arrows or the exponent on the left. But for you, I'll use the exponent on the left. Okay, like exponentiation, it's repeated multiplication. Oh my god, repeated multiplication. Exponentiation, no, titration, it's repeated exponentiation. So like I'll make an easy example. 4 titrated to 2 is 4 to the power of 4, which is 4 multiplied by itself 4 times, which is 256. And the titration grows really quickly, really fast, even when with kind of small numbers, like 2 titrated to x. And we want to see the value of x increase and the result go very exponential. So 2 titrated to 0, I think it's 1. 2 titrated to 1, it's 2, because it's just itself. 2 titrated to 2 or 2 pentated to 2, the same thing. It's 4, easy as it sounds. Then here it starts to get a little bit bigger. 2 titrated to 3, it's 16, and then already the big boom. 2 titrated to 4 is something like 65,000, and it just exploded in a moment. But we can only define titration with natural whole numbers, 0, 1, 2, 3, 4, and so on. Why not fractional numbers like 1/2? What is a number titrated to 1/2? Means exponentiated to himself half times. That is the concept, because we have to keep the rule where I think it's like f(x plus 1). It's ugly, I know. I'm writing with my hand. Plus 1 is x titrated, no, like a number titrated to himself x times. Exponentiated. Okay, sorry. So we need to keep that rule in, like, not exactly. So what I have defined for you, for people, for also with imaginary numbers, and I think complex ones, but not quite negative ones, is the concept of another formula I talked in another video. You want to see ra of x equals 1 fraction x. What does this mean? Very easy. Like ra2 equals 1/2. Ra 1.4 equals 2.5, like that, because the exponent goes the fraction goes the other way around. So what I have done, like let's say 4 tetrated to 1/2. Okay, that it's 3/2, so it's 1.5. I hope you understand. Let's write it like here in the corner. First we look at the value of 4. 4 tetrated to 1 is 4. 4 tetrated to 2 it's 256. So there must be a middle one. Now what I asked ChatGPT, and he suggested like fixed point arrangement, and I think the value was 130, but it's wrong because it used the intersection points. So if you do 4 tetrated to 2, the passage to 4 tetrated to 3, and you do already 4 tetrated to 2.001, the result is already big and does not follow the pattern, the function I showed you, very popular. So 1/2. What we'll do is we take the floor. Let's write floor FL. So you know how a floor number is. It's like floor 1. No, non-floor, not floor. Sorry. Ceiling. I think ceiling 1.1 is 2. Also wrote as like this. We're gonna write it like this. So what is floor 1.5? It's 2. So we are keeping 4 tetrated to 2, and we'll just write for simplicity 4 to the power of 4. Now this isn't exactly what we wanted, so we need to scale it down linear, like a graph, like brrr, here it goes. What we're gonna do for this case, it's easy. There are 2 versions, both of them are equal, but the second one I will propose, it's easier, and the one I used. We have to do ra, the other part missing, so 0.5, which I said it's 2. So the the square root. So let's just do the square root, which is 4 to the power of 2, which is 16, and it's technically it's linear, not a point fixed arrangement, which is bad. But the same case as I said, you just keep 0.5 and you add an extra exponent with parentheses up there. You calculate something, 2 equals 16. Let me try another example for like a crazier one. Seats tetrated to 1.3. I mean, it's alright. So we take the ceiling, it's 2. We now have seats to the power of 6. The extra exponent goes there. We calculate. We need to use cultures. I'm sorry. I will show it in a moment. Seats to the no 6 to the power of 0.3, and good enough. This is alright. It's linear, not exploding or going crazy. It's approximately 21.479. Now I'm gonna show you in a graph the values of 2 tetrated duets. Alright. Good enough. I have no. Yeah, don't worry about ChatGPT. I was asking them about the values. So here is Desmos. What I did was convert each one to a point and out close to make them look like a graph. We have all the values here. Like this is, I know I made much. This is 1.07 and so on. Now this is not fixed point arrangement where it just goes crazy and does not respect any rules, any linear growth. This is a bit like of a parabola, but it's too much. So we plug in 2. No, we plug in 1 and we get 2 as usual. 2 tetrated to 1. Then we plug 2 tetrated. Oops. What have I done? Okay. 2 tetrated to 2 and we get 4. Alright. And this continues. So already you see it starts growing much. 2 tetrated to 3, it's 16. And if you calculate 2 tetrated to 4, like I said, it's about, like I have it right here, 65,536. So you look at this graph, you have all the points here like a parabola. Then we're gonna compare it to x squared. Then the points become more and more distant till it becomes giant. And finally, here it is. Now I stopped here because if I plug in like 4.1, I think the result is gonna be crazy, like millions after just a bit. And the 2 tetrated to 5, it's something big, very big. So I'll give you a moment to look at this graph. Now we're gonna do we're gonna squeeze it down till we get to the last point. Where is it? Not yet. Okay, you have all the points squashed here, very close to 0, but not actually. Now let's return to normal. Let's do f of x. Sorry, it's Italian. I am Italian. You know, but by my pronouns and my the screen. Like for every Italian watching, ciao. Forse adesso non mi capite, ma vi chiederei di lasciare like e iscriverti, perché io da grande voglio essere un matematico e ho creato per una formula, l'ho messa su un canale, sul canale. Ok, let's do squared. Let's see. So the iteration already starts off strong. then it's losing even more, then it matches that, and then it completely backfires. But then out of nowhere they regain again and they explode like crazy. Just for comparison, let's see. Yeah, it still has a long way to go. But I don't know yet how to find imaginary negative numbers. I think it's quite easy. I could do that, but I don't want to right now. So we're gonna look at imaginary numbers. Let's reopen cultures. Oops. Okay, let's say no. I will write it like this. Okay, let's put I. What is 2 tetrated to I? That is actually pretty easy. So you want to have the real and imaginary part 0 plus I, which is just I, and then we use the same thing. Let's put 1. So we have 2 to the power of I, which is this number right here. It's a complex number. But what if we want another number, 8 tetrated to 2 plus I? No, it's not this result. Okay, so we use the same thing. Well, that's a pretty big number. 2I. And good enough, it scales down to okay. It's like the sum of sigmas. 1 plus 2 plus 3 plus 4 plus 5 plus 6, so on. And you extend it with the famous one, like, oh my god, let's use Desmos again. We'll save this. We're gonna put x squared. No. Well, this is just an example. X squared plus x 2. You can extend the formula for 1 plus 2 plus 3 plus 4. Like let's put we plug in 15. Now easier. We plug in 10, we get 55. Where is it? Boom, right here. Now just for curiosity for me. Ooh. This is cool. Okay, this is enough of my talking. I hope you like this video, and let me know if you ever try to, because this is my example. I think it's great. It works very well because it kind of respects the tradition itself. But let me know in the comments what you have tried Bye.